subjects that some humanities and social science, economics, and again, mathematics with all this general stuff to save time and money by skipping them. In this one case, we apply AP credit and SAT credit, especially for chemistry and math. Like, I know I AP credit for math, so I was going to skip some of that, but I didn't have AP credit for chemistry. And chemistry, let me say that course didn't go through, but basically, you can also apply a proficiency test when you actually get to UOI. There's this proficiency test that you can take in the beginning of the school year, or at the end of every semester. And it depends, it's mainly for the very low level courses, like physics and chemistry and then math. So you don't need to ask your advisor on that. But it's pretty easy to register for. You take it a week before, then you can take the next class in the sequence. And finally, a good alternative is just take a equivalent of local community college. This is really applicable for, say, mechanics, thermodynamics. It's not a higher level, or even some of the lower level technical courses, as well as some of the agendas that you can take them for much less cost than it would be to take it as you apply, both during school year and during summer. And so then you can take more, you can get to the fun classes sooner, number one. Number two, you don't have to do this at your this speed. Get to the fun classes sooner, as well as Steve discussed on that. So again, the aerospace courses at UOI, that it is very universal constantly. It's going to be different at other universities, but again, a lot of these are just basic introductory courses. One is introduction to aerospace engineering, basically, which I do, and of course, it's assistant for. So generally, it is getting on the same knowledge point. So it's a lot of introductory lectures on this is the rocket. A rocket goes up, the rocket flies in a ballistic in an arc. And it's also centered around group projects. Two group projects, one rocket and one battle project. And then there's creative design, which it should be standard in most aerospace courses nowadays. And this is actually the final project, my final project for the course that I made in using CSNX. Which again, has software like SolidWorks, like Autodesk Inventor, and they're all roughly comparable to each other. So if you know one, you know all of this speed. It's relatively easy to transfer over. Again, flight mechanics, I just think that this semester is about basic aircraft, spacecraft, trajectory and movement, and all the general stuff that you should know, as well as basic systems design, general integration of on reverse, and then for the last 2 years, you ended up with some more fun ones. Like now, these are the regular courses that you have to sign up to take aerospace engineering for. Things like aerodynamics. For UOI, it's split up into inconversible and conversible flow. One for non-supersonic and one for really fast flow, like over Mach 0.3. There's also dynamics and controls, like this is from the controls course I took last semester, or rather that just finished right now. This is the final project of a drone race, basically. We're programming on the controller to get this drone fly through the wings without crashing into them back between the other drones. So that's a really fun project. There is a lot of writing, of course. And then there's also general structures and propulsion, and of course all different topics that make up aerospace engineering. Now, you also need to take a couple of electives for as well things like they have like a courses, not a lot specifically for space. To be honest, there's orbital mechanics, there is the propulsion, and this year there are hypersonics as well. So again, the selection of electives changes year to year, but it generally stays mostly the same. And of course, the highlight of a lot of this career experience is senior design, where you actually get to design a theoretical aircraft spacecraft using systems engineering to choose different parts, choose the geometry, and try to integrate it to a functioning vehicle. And I do know if you are in the air side, where you're going to make an aircraft, you actually can submit your design to a aircraft way is the professional organization for airspace, and you can actually win an award if you do the air side senior design. Now, of course, we get to extracurriculars. Now, the big thing about extracurriculars is that doing academics may be all fine and dandy, right? But then now we have extracurriculars get the little extra boost to your knowledge and to your skills. It basically gives you a lot of technical experience, technical leadership experience that you may not get in your class. It makes you help you stand out from the others. And it should companies they love to talk to these registered organizations or ourselves. And they will, and some ourselves like I just will often invite companies like Cox Aerospace, like Blue Origin, to come talk to them and recruit. To get some time recruited for like an hour is great. And you know, I would really recommend joining at least 1 hour or so to get knowledge of things. And again, with ISS, we have 5 different technical projects or general areas we're focusing on. Like, one is our large rocket acquisition group, it's called SpaceX, where our goal is space. So we're constantly innovating and doing new advanced, very light rocket suite. When we can bring up our goal is during up in the summer, and we hope that 100 kilometers in the next 2 years or so. And of course, there's also 2 NASA missions that ISS could be sent Roscoe Apogee. One is mission design, one is actually manufacturing tools for astronauts. And they can test it in the NASA's neutral buoyancy lab, where there's basically a giant swimming pool that's meant to simulate how people would work on Earth. People will work in space, really. So that's ISS, that's the team's a bank sensor that's being tested out in Johnson Space Center in Houston, I believe, is where it's located. Of course, we do work on our own hybrid, solid and hybrid rocket engines as well. And we do a lot of outreach to other, like, elementary, middle school, and high schoolers as well, to raise different competitions and outreach events as well. Some other kind of technical RSOs include like the operators and turbopump that the predecessor of this organization made, and they're going to put like a liquid engine for a liquid rocket. It's supposed to be doing really cool stuff, doing a lot of metal 3D printing as well. Of course, there's student aircraft builders, and this the design by competition drone. They basically build a competition and they course, Iris and a bunch of different car teams. Things like Solar Car, Atlanta Motorsports, all these different teams that give a technical experience. So similar virtual articles that I should probably mention. Things like slightly women engineers. In addition to being a good place for resources and networking as well, there's some great for scholarships as well as they do professional or technical work as well. University and one universities managed industries, these are companies for professional resources. If you need like resume review or if you need like help in navigating the work the area, you can go to these places. Again, think of how to get internships is to have these technical experience and have like any technical experience really for your first internship. Any technical experience works as long as you can present it in a manner that makes you able to like explain it well and your role well. Like if you're able to answer questions in this situation, task, action, and result formats, then you should be able to answer them well. And again, apply to literally everyone. Any and all experience is good. This is why I love at a truck company right now. Like, I'm an engineering major at a truck company. And that's still fine. That's still a good experience that you have. Some good. And I know I got my admission through applying at a career fair recently. After this recruiter, I put him down as a reference on the. I'm trying to apply. I put him down as reference on the admission application, and then I passed the interview, and then I move up. Also, in addition to giving like a lot of free stuff, like I got like free bags, free pens, especially. It's good ways to practice your interviews as well as, and also there's a lot of help available for career services, including career service and especially upperclassmen. In my experience, people are really willing to give you help on this if you reach out to them. And there are plenty of opportunities as well to get this help. I know ISIS does resume reviews every career fair, so does engineering career service. And engineering career service, in addition, is open like give you an apartment anytime and then get advice from the people who are paid to help you get jobs. And here's a very simple resume. I don't think we're kind of focused, but we can come back to this in a month. Now, I'm going to research. Now, I haven't yet done formal research for a professor, but what I've heard research is basically just in it. Think about a professor as this is on the lab meetings, like do so I like your research. Name exactly why you like your research, and may send up in a research meeting to see what it's like. Just ask them to sit in so like a very low, it's a lower bound, very educated, asking for it. Like it is any open positions in the research group. Just being able to sit in and then see what it's like. And then once you sit in, you get a better idea of what exactly you're asked for. There's like a lot of formal courses for research, some semester long, like pure and introduction research class for aerospace. These are two things that I would participate in. I think that just forgetting that general research experience at a very relatively low commitment than say a professional lab. And then there are a bunch of programs that I need links to the link up just in case. I'm gonna come back to this. Of course, graduate school. Now, there's a bunch of different reasons to go to grad school, which I got from a third grad school program at PhD research. Told me about a lot of this. Like, some reasons are you want to learn more, gain knowledge, and in general, going to grad school helps you stand out and improve your competitiveness in the job market a little bit, especially if you gain some knowledge that you're able to transition to like a specialized subfield. Like say, I'm doing a lot of research for human right now, but I may want to go. I want to go say aerodynamics. I can do my master's on aerodynamics stuff, and then now I can do aerodynamics and structures. And of course, getting a master's helps you like understand the boundaries of the field, which is really good for going to like a doctorate degree as well. It's also really good for say yeah. There's a grad school. There's a bunch of different ways that you can do the grad school in, like for master's degree, there's a thesis track where basically you either do research or you can write a thesis at the end of it on a project which generally like undergraduate research. This is like an extension of that, and that usage is like it's not really like out there. It's not a lot of what synthesizing this research with two different topics together and see like the intersection of those two research. And the big benefit of becoming a thesis is like you're able to get I think you have assistantship, then also just get a write a thesis and get a research mentor. So you need a professor to basically like sponsor you, sort of. Non-thesis, we don't get any assistance, but you don't have to write a thesis. So a lot of companies like to pay for that, just for you to get a master's degree. And of course, there's this new master's degree in electrical system engineering, which is a bit more focused towards general design than a traditional master's. And again, not that if you want to be the subject matter expert of part in electrical engineering, like I've heard people who have done all the computer excited research, but then they go and do the research in the industry as well. I've heard of someone who did research on this new type of aircraft. Then they went and did research for that at Boeing in their advanced research project division. So, getting PhD may unlock doors, but in the end, it's a very long and very hard, it's a very long track to get there. So that, before I wrap up, I want to say that going into aerospace, there's a lot of jobs in defense, like a lot of jobs that want in aerospace, a lot of the military and defense. So, before you do executive in aerospace, you should probably ask yourself that if a push comes to shove, are you willing to do a defense job? Which is fine, it's fine. But you should probably get that sorted before you email at LinkedIn or whatever. Yeah.
All right, thank you so much. All right. So, what do you guys think? You guys like that? Yeah? I love it. All right. So, next up is our very own TAS incoming Vice President, Brendan Rogers, talking about a research project he did that was an particle accelerator proposal simulating cosmic rays on planetary atmospheres, if I'm remembering that correctly. It's going to be a super cool talk, so get excited, and here he comes right now. Let's give it up for Brandon. Wow.
That went flying. Okay. It should be out the back.
That was a great start.
Right there. There we go.
Gotcha. All right. You got that mic when you're ready.
Gotcha. Wow.
We're off to a pretty good start, guys. How are we feeling so far? Yeah? I just want to say thank you so much to all of you for coming out to this event. This is the first time TAS has done something like this, and we are just so incredibly thankful for such a dedicated group of students coming out to support our club, especially with new ground being tread in this area. We hope to continue doing things like this more often, but this is a test case, and so far, I couldn't be happier with how it's turning out. But as soon as my laptop starts cooperating, we can get moving. I love you, Gar. Okay. Can I get a charger? Yeah. Nurse Angie has one that I can use. Yeah. So my laptop is a little dead right now, like a lot of us after this hell week. So while I'm waiting to get a charger so everything can get moving forward, I think I'm good, Gar, but thank you. So I just want to introduce what I'm going to be talking about. So over the course of about 4 weeks, I had the absolute privilege of doing a research project with our very own Dr. Hawker for the CERN's Beamlines for Schools research competition. Now, this research competition is an international competition that is open to high schoolers around the globe. I believe this year, 60 countries participated with over 400 proposals being submitted, IMSA being one of the schools that submitted one from the United States. On average, about 20 proposals come from the US every single year. This was actually the 10th anniversary of the competition, so it was a great time to get in on the action. Yeah, let's see. But, good. There we go. All right. So, like I said, I had the absolute privilege of doing this competition with our very own Dr. Hawker and a group of so many talented individuals, all IMSA students who just came together voluntarily to work on this project with me. So our team was composed of over 24 IMSA students, all of them juniors, who took time out of their day almost every single day after school for hours on end. I think thinking back to how our meetings panned out, usually it was 3 hours every day just working just to bring this project to fruition. So the overall product of our work was a research proposal that we submitted for the competition. It was a written proposal, and the link to that proposal is with that QR code. So if you would take the privilege of just scanning that, if you'd like to follow along with the actual written proposal that's on its way to actually being reviewed by CERN right now, it's right there. But like I said, it was an absolute privilege working with these wonderful groups of people for 4 weeks in the middle of class season leading up to APs and the SAT. So it was a hectic ride. But, so just a little bit of an introduction on who I am. So I am Brandon. I use any and all pronouns. I am IMSA class of 2024, a proud junior, even prouder member of Hall 1503. And the thing I have most pride in, and is the reason I'm up here today, is because I am a proud board member of our own Titan Astronomical Society. I've been a board member for the last basically 2 years, and it's been some of the greatest experiences I've had on this campus. Being able to work with our entire board, from our current sophomore representatives to the junior representatives I've known my entire career here at IMSA, to our senior representatives who I can't let go of because I will miss you guys to death. But it has been an amazing ride, and I can't thank them enough. Outside of being a board member of Titan Astronomical Society, I also write for our school science newspaper, Hadron. I'm a member of our FRC robotics team, and I am a member of our a cappella group here on campus, Mod 21. I've loved to sing since I was a little kid and loved music even more. But my motivation for going into astronomy, participating in tasks, becoming a board member, is because I have been a lifelong lover of all things space related. Space science has just been in my bones, and I can't let go of that love. And I don't think I'll ever let go of that love, because it drives me to look up at night, because there's just a wonderful, beautiful universe out there to see. But just one fun fact, I own 4 telescopes at home. One is on campus right now, but 2 of them I bought, and 2 of them I worked and built, one of which is fully 3D printed. It's not a really big thing, but it was a cool experience to work and build a telescope from scratch using a 3D printer. But, so what I'm going to be presenting on is my experience working in a research project for the Beamlines for Schools International Competition held by the CERN Particle Accelerator facility in Switzerland. I won't be going into too much detail about the competition itself, because that's not really the focus of what I'd like to present on. I'd rather present on the relation the topic we researched about has to wider astrophysics and astronomy. But just a little bit of basic information for the Beamlines for Schools competition, so we all are on the same page. High school teams enter this competition by creating a scientific proposal for a particle accelerator experiment they'd like to actually perform at CERN. This proposal is relatively short, with a maximum of 1,000 words for a proposal of the experiment. You have to describe what your motivation is, what your team is like, what your experimental design is, what materials you're going to use, what detectors you're going to use, what's the overall science behind it, what's the overall physics behind it, why exactly you're going to attempt to do this at CERN instead of another particle accelerator facility that exists out there. But the experiment can be literally anything that you can creatively come up with that has some relation to a particle accelerator. If you can come up with an experiment that's within the fields of biology, but utilizes a particle accelerator as a main focus of the experiment, that's a totally valid proposal idea to submit. I believe 2 years ago, a team even submitted a proposal in which they were going to test the effects of cosmic radiation on neural tissue to see what effects that had on brain chemistry and things like that. But The experiment can be basically anything you can set your mind to, but the top winning teams, this is the coolest part in my mind, the top 3 winning teams actually get to go out and be flown out on a fully expense-paid trip to conduct their experiment at either CERN or another particle accelerator facility. The trip is completely expenses paid. You get to do research at the facility itself, talk to the physicists who run the facility, talk to the physicists who are going to be walking you through how to conduct your experiment, and actually gather data and perform the experiment at an actual particle accelerator. And that's what we're gunning for here, to be one of those 3 winning teams to go and test their experiment at a particle accelerator, which I can't tell you how cool that is, because there's really no other opportunity to do this in terms of being in high school. But this opportunity, when it arose, I jumped at it and wanted to get as many people involved as possible. So there's a lot of passion behind what we were doing over those 4 weeks. But our overall proposal was to investigate the effects of cosmic rays, which I'll go into a bit more detail on what they are in the next slide, of varying different sources, different astrophysical sources on the atmospheres of exoplanets and our own planet, specifically our old atmosphere, our primordial atmosphere that formed right after our planet formed. So through the use of a particle accelerator experiment. So the 2 images there represent basically the 2 areas in which we're looking at when it comes to this experimental proposal. On the left is a planet with a relatively thick atmosphere and a chemistry that we were investigating in our experiment. And on the right is a image of a cosmic ray shower as it's hitting the Earth's atmosphere. These 2 areas of study were kind of the forefront of what we were looking at when it came to creating our experimental proposal. But cosmic rays are a very, very cool area of astrophysics because it cross-cuts into a bunch of different other areas of physics in general, specifically particle physics. So our research project focused on the investigation of possible cosmic ray-induced amino acid production within simulated planetary atmospheres. So cosmic rays are basically really, really high energy particles flying through space at a massive fraction of the speed of light, faster than anything that we're able to achieve here on Earth with our current particle accelerator technology. And these particles are flying through space, being flung out of a variety of different astrophysical sources and flying towards the planets within the wider universe or into stars and just bombarding the whole of our galaxy and our solar system with cosmic rays. If you look at the figure right over there, that shows the overall atomic makeup of a cosmic ray. So most cosmic rays are protons or hydrogen ions that are being space at incredibly, incredibly high speeds. As you go heavier on the atomic scale, heavier on the periodic table, you get less and less of those abundance peaks at hydrogen atoms and goes down as you get towards heavier elements like iron, nitrogen, stuff like that. But the overall interest we had in cosmic rays is because cosmic rays are constantly bombarding planetary environments and the atmospheres of our planet and all planets within the wider solar system. So cosmic rays are coming out from a variety of different sources, but the fact that they're always hitting our planet means that the effects that they produce are a constant, continual process that we can experiment on and understand how those processes were happening when the Earth was initially forming, if that process is continual, which cosmic ray showers are. So when it comes to the overall physics of cosmic rays, there's a bunch of different sources that you can find when it comes to where the cosmic rays are coming from. One of the largest sources of cosmic rays close to home, and when I say close to home, I mean in our solar system neighborhood, is the sun itself. The sun is an incredibly energetic object, and it's flinging out hydrogen ions out of its core through the multiple layers of the sun out into space with the solar wind, which is bombarding Earth and other planets. The solar cosmic rays on cosmic ray scales are relatively weak, meaning that when they hit our planet, they're usually deflected by our strong magnetosphere, meaning the majority of the flux we see of cosmic rays on our planet aren't from the sun, but are actually from galactic and intergalactic sources, either within our galaxy, so really, really high energy nebula that are formed from supernovas that are still spewing out high energy particles after the death of that star. That's the Crab Nebula, if anyone has a really good eye for spotting astrophysical objects, or from the hearts of galaxies, supermassive black holes that are spewing out high energy particles due to their incredibly active nature, spewing out these cosmic rays at incredibly high speeds. These two sources, either within our galaxy or outside of our galaxy, form the bulk of the sources that are predicted to be producing cosmic rays. But the main process that makes cosmic rays interesting is that thing at the far right. Basically, when cosmic rays hit our atmosphere, since a proton is a composite particle, it undergoes what's called a strong force interaction and breaks apart. When it breaks apart, it showers in the upper layers of the atmosphere. Those products continue to fall down. They shower. They produce more products until you have a huge showering cone of a bunch of produced particles that fly towards the ground. Now, to get a sense of how constant and continual this process is, the lowermost products of these cosmic rays, which are called muons, heavier versions of the electrons, a muon produced by a cosmic ray goes through your head every 2 seconds. So if you count 2, a muon has gone through you from the showers produced by a cosmic ray. This process is happening continually every single hour, every single minute, every single second, producing these showering effects, which these particles fly down in the showering effects towards sea level. And for our experiment, since we were looking at simulated planetary atmospheres, specifically simulated planetary atmospheres at sea level, we were specifically looking for the particle products that are found at sea level, which are those muons. So the overall design of our experiment, which we submitted in our proposal, was to basically produce a beam of muons that simulated the characteristics of the muons that are produced in cosmic ray showers. So when a cosmic ray showers in the upper atmosphere, breaks apart, and flies towards the ground, those muon products drift towards the ground at incredibly high energies and go towards sea level and actually fly through the crust and are detected by underground detectors, which is why we know muons are flying through the atmosphere after cosmic ray showers. But since we want to figure out what effects cosmic ray showers have on atmospheres at sea level, we want to simulate muons. So our experiment used what's called a collimator to create a shower of muons, then to filter out the muon characteristics that we liked, certain momentum values, certain energy values, certain spread of muons, and let it go through the rest of our experimental setup. So if you look at the one there, the initial beam of protons, which is produced by the particle accelerator, hits a very dense target and showers just like it would in the upper layers of Earth's atmosphere. That proton that's being produced by the particle accelerator would be at an energy level equivalent to the energy levels that we see cosmic rays coming at when they hit our atmosphere, even though we can't get it up to the exact levels of the energies that they hit our atmosphere because nature's got us beat on that. But when it hits that target, it's going to shower out, and those two block things, labeled by the 2, are collimators, which basically close up and only let a certain type of particle through. In in our case, we only want to let the muons through. Those muons, my bad. Those muons fly through the collimator and hit what are called scintillators. Scintillators are a type of particle detector that basically tells the rest of the experimental setup to turn on and to start collecting data on the particles flying through. So the muon flies through the scintillators, and then it flies through what are called drift wire chambers. They measure the position of the muon as it goes through the rest of the experimental setup. So when we get the position of the muon, we know where it was after it's produced from those collimators, and then it hits what's called a bending magnet. The bending magnet induces a magnetic field around the muon, and since a muon is charged, it has a negative charge just like an electron, it's pulled towards the positive end of the magnet. Now, depending on the momentum of the muon, it's going to be pulled a certain amount. That's where the second set of drift wire chambers come in. That second set of drift wire chambers measure the new position of the muon and see where they are compared to the first set of drift wire chambers. Depending on where those muons are in the second set, we know what their momentum is because they shifted over a certain amount because of those bending magnets. Now we know the position of the muon, and now we know the momentum of the muon, so we know how much energy it's going to lose as it goes through the sixth part of our experimental setup, which is a gas target filled with a gaseous mixture that's supposed to resemble the early chemical composition of Earth's atmosphere. So when it comes to that gas composition, we wanted to create a gas composition that was supposed to resemble a transitionary period in Earth's atmospheric history, basically when it was transitioning between a incredibly methane-rich atmosphere to a CO2-rich atmosphere, which would then transition to our O2-rich atmosphere as biotic processes take over and cause oxygen to become prevalent in our atmosphere. So we had a good mix of a bunch of different gases that could produce amino acids. So going down the list, we have methane, carbon dioxide, carbon monoxide, nitrogen, ammonia, H2, and a bit of water vapor. Now, the significance of the gases that we chose is because in previous experiments that looked at similar things to what we're looking at, the main focus they needed was a source of carbon and a source of nitrogen for the muons to lose energy into, and that loss of energy would cause an ionization of those gases, which would then produce amino acids. Now, the significance of that I'll go into in the next slide, but we wanted to make sure that there was a source of carbon and source of nitrogen, and those sources of carbon and nitrogen were lined up with the expected carbon and nitrogen sources that were in Earth's early atmosphere. The rest of the stuff is just some values that we needed to have for the actual experimental setup. The partial pressure is basically the concentration of everything. As you can see, the concentration of everything except for water vapor is equal. There's a bit of a typo for H2. It should be 20,000 just like the rest of the expected values. Ionization energy is how much energy you need to ionize one atom of that particular gas. And then the minimum ionization energy is how much energy the muon itself has to impart into the gas to ionize it. So as you can see, for a lot of these values, they're high minimum ionization energy, meaning we need high energy muons to fly through the gas and deposit their energy inside. That's where we get to that second to last row, which is a value that gives us how much energy the muon is losing over a certain distance. So depending on the gas composition of which the muon is moving through, the muon's going to lose a certain amount of energy. The more energy that muon loses, the more that gas is going to get ionized. The more ionization, the more likely we're going to get amino acids to be produced. And then molecular weight is something that's tangential. But the figure next to that table is just the basic design of our gas target. We wanted the gas target to be in a cylinder as to ensure that no muons just flew out of our target and that it would be easy to measure muons that are flying through the gas target. But as those muons fly through, they will deposit their energy, ionize the gas. That ionized gas will undergo chemical reactions that could produce amino acids. Now, the importance of amino acids is relatively obvious. They are the building blocks of proteins and therefore the building blocks of life. If you have a process that continually produces amino acids within a planetary environment, you have a means of producing the necessary building blocks for life on a planet, meaning cosmic rays could potentially be the life bearers of the universe, imparting the necessary energy for chemical reactions to produce amino acids and therefore produce life to occur regularly. This is really, really, really important. If we are able to validate this hypothesis, i.e. go and test it and actually see that there's enough ionization energy loss to ionize the gas and produce amino acids, we would be able to verify that there is a continual process that's occurring in the universe that's able to create amino acids out of just disparate gas in a planet's environment, meaning that planets can have a continual sink of necessary organic compounds. But that's basically everything I wanted to run through with you guys. This was an amazing experience to be able to work with those over 24 IMSA students on this experimental proposal, and none of this could have been done without them. The idea, the execution, and the design were all a collective effort, and I can't thank those people enough, and I can't thank you guys enough for coming and listening to our speakers so far. So thank you.
Thank you so much for our two speakers. Right now we're going to be having a short 10-minute intermission, so make sure to stay tuned for our next speaker. Thank you.
Okay, I'm talking. Can you hear me? Is it coming through the system? Testing, testing, 3, 4, 5. Testing, testing, 3, 4, 5. Is this thing on? Okay. All right, testing, testing. Very good.
Are you guys excited for our final speaker of the night? I know I am. Next up is Jim Hopkins talking about the origin and evolution of red and white dwarf stars, or the astronomer and his 7 dwarves. He's been an astronomy professor at the high school and college level for over 45 years. He does astronomy outreach and has over 4,000 hours of experience observing out under our very own night sky. Give a warm welcome to Mr. Hopkins.
Thank you, ladies and gentlemen. Can you hear me okay? Eve has me all rigged up here, and if I get electrocuted and fall down, you know who to blame, okay? Is there a way to get the spotlights dimmed down a bit here? Because I like to actually see people who may have a hand up or something as I'm going through my little spiel here. As you can see, I was told anytime you give a talk in physics or astronomy to have a spiffy title that's an attention getter. Well, this is all I could come up with. Eve's father asked me if I could fill in for a speaker who did not show up or could not show up tonight. And with 5 days' notice, I said, why, sure, Sean, I'll be glad to. And all I needed is a few details. Things are going to work out just fine. This talk I have given before. Sometimes I go back in and tweak some slides just to make sure everything is kosher, but I think we're in pretty good shape here. Okay. No talk about stars is complete without understanding this graph. It's in every astronomy book I have ever opened, and that's both high school and college. They have different versions, but we are dealing with 2 astronomers, Einar Hertzsprung, who was Danish, not the kind you eat, and Henry Norris Russell, who was an American, and independently they came up with pretty much the same idea and didn't know it until they read each other's published reports. Well, what we're doing in all cases here is taking something on the y-axis which is called luminosity, or if you will, brightness, and it has to have some kind of units. Normally it's absolute magnitude, but this particular slide goes magnitudes compared to our sun, and it is logarithmic, because our sun is across from 1 right here, and everything is 10 times brighter as you go up to 1,000,000 times brighter than our sun, or gets dimmer as you go down to 100,000 times less bright as our sun. On the other axis, you can put any one of 5 or 6 different variables on the screen there, and typically spectral class is one of the first. Raise your hand if you have never heard of spectral class. Okay, we have a few honest people in here. Very good. Spectral class was done by the computers at Harvard in the 1907, 8, 9, 10 area, way back when. And one of them, Annie Jump Cannon, was specifically told to study spectra of stars and come up with some system. And they told her because they didn't want to do it themselves. So they dumped the tedious work on some of the women who worked there that were known as computers. Well, she came up with a system that starts with O, and by the way, there is no sense whatsoever to the 7 letters she chose. But O, B, A, F, G, K, M are the letters going across the x-axis. And I don't know, I learned this in 1962 in an astronomy class. Yes, I'm that old. 1962 in an astronomy class, that you can remember those if you remember, oh, be a fine girl, kiss me, or something to that effect, okay? So spectral class, each has its own characteristics, and we'll be discussing these a little later on also. By the way, if you would like to have a copy of an HR diagram, I have 20 handouts here for those of you who really want it. If all you're going to do is throw it in the trash can on the way to wherever you're going, just leave it there for somebody who might need it, because I don't have as many as I probably need to. But anyway, if we're not talking spectral class, we could be talking color. And I think all of you know that as you heat up, for instance, a metal, its color changes. When it's the first thing that your eye can detect is that it looks reddish. And as you heat it more and more and more, it becomes shorter and shorter wavelength until it's blue. And most objects on Earth, by the time they get to blue, have melted whatever you're heating up anyway. So blue temperatures start at about 30,000 kelvins and can go much higher than that. We also have temperature. Besides color, we have temperature. And the coolest stars that we're going to be talking about are known as main sequence stars, M dwarfs or red dwarfs. And main sequence stars have one function in life, and that's all. Convert hydrogen to helium in the core. That's all they do. That's their job. Okay? They don't do it really well because there is no true core in a red dwarf. They are totally convective. So the helium that is produced by hydrogen in the proton-proton process simply flows in the interior of a red dwarf. And sometimes it's near the core, and sometimes it's somewhere else. But in our sun, we have layers like the core, the radiative zone, the convective zone, the photosphere. That doesn't exist in a red dwarf. They are truly convective, or if you will, thoroughly stirred. Okay? Stirred, not shaken. Yes. All right, a little Bond joke there. We can also talk about solar radius. What size are these stars? And again, we're relating it to good old sun. And for those of you who forgot the number, our sun is approximately 865,000 miles in diameter. So if you cut that in half, it's about 400,000, 430,000 for a radius. And those are English units, miles. If you want to do it all in metric, feel free. Besides the radius of the star, we also have the lifetime. How long do they live? And as it turns out, stars form at different rates, and they burn their fuel at vastly different rates. In fact, fuel consumption is a function of T to the fourth power. So if you have star A that is 10,000 degrees, and you have star B that is 20,000, the difference, this is twice that, and 2 to the fourth is 16 times. So the fuel consumed in star B would happen 16 times faster than in star A, which is extremely quickly. For that reason, some of these stars don't last very long. The hotter the star, forget the surface, we're talking about core temperatures. The hotter the core temperatures, the faster the fuel is burned, the faster they evolve into something else. But some of the stars up in the blue giant area of the main sequence, even though all they've been doing is converting hydrogen to helium, they're doing it at such a rate they might only last 2 or 3 million years. Now, in comparison, our planet is 4.6 billion years. So our planet is maybe 2,000 times older than these stars that just burn their fuel at prodigious rates. And in doing so, they are 80,000, 60,000 times brighter than our sun. So we're not talking that end. That end is for another talk. This end is where we are tonight. We are down in the red dwarf area. And we also know that the pressure from gravity on these stars is pretty low compared to any other spectral class. Therefore, they don't burn their fuel real rapidly. To quote a friend of mine who's into cars, they get better gas mileage. In fact, a red dwarf might last for 1 trillion years. We're not going to last that long with our sun. We have about 5 billion more years. That's what the experts tell us we have for our sun. So when you're talking a red dwarf, you are talking about an extremely long-lived star. And the objects that you see up here are stars that evolved off of the main sequence. They're no longer converting hydrogen to helium. In fact, in the area of giants, they may be converting helium through a triple alpha process or through the carbon cycle to where they're going straight to carbon from the helium they produce. And hydrogen, that process, proton-proton reaction chain, is just not very important at higher temperatures. So as they grow, two things happen at once. The core shrinks, and the outer part of the star swells up, and what's going on is now carbon and usually oxygen are being produced and stored in the core. And you may have heard of carbon stars. Most carbon stars are either red giants that are producing more carbon than oxygen, and or they could actually be on the other end of the evolution stage and just simply be red for the time we're looking at them. If you look at them again on 100,000 years, they would probably be white, but at this time they're red. If we start up here a little higher with more mass, and by the way, the stars up here have up to 60, 70, even 100 times the mass of our sun. Down here, the red dwarfs or M dwarfs are usually around a third down to a tenth of the mass of our sun. The greater the mass, the more pressure on the core, shorter the lifespan because they burn their fuel much, much faster. And if you start up here and you burn up your fuel and go to the next stage, instead of a red giant, you're going to become a supergiant of some color. Some are red, but not all. Red supergiant, some of the largest stars known. But we also have a very well-known star right here, which is the North Star Polaris. That is a white giant, or if you will, a yellow-white giant. We have Rigel, which is the left kneecap of Orion, and we have Deneb, and Deneb is part of the Summer Triangle. It is the furthest north bright star in the constellation of Cygnus, okay? So these are just typical, some of the giant stars. And we're going to ignore almost all of that. That's, again, another talk. But when stars leave these, either by supernova or by producing planetary nebula, and their cores survive, the cores shrink. And they shrink and they shrink until they're down into white dwarf land. Now, a white dwarf is actually the remaining core of a much larger star. It is almost entirely carbon and oxygen. And there may be some helium in there, but most of it is oxygen and carbon. These things shrink down to the size of our planet. So think about a sun-sized star, or larger, that as it blows off its outer layers, the core is shrinking, and it turns white hot as it's shrinking under gravitational pressure. And then we end up in white dwarf land, which, as you can see down here, might only be 1/100th as bright as our sun, or Procyon b here is about 1,000th the brightness of our sun. So this is a general statement up here. So if we want to sort of do real quick categorizing, a blue giant star is a main sequence star, and if you read down, it may be 100,000 times the diameter of our sun. And if we keep coming down here, it's blue in color because of its temperature, and it's more than 30,000 degrees on its surface. And generally, these are Kelvin, okay? 30,000 Kelvin. You can go on the other side and do the same thing with the red dwarf. Just kind of read the characteristics downward and see what you get. Okay, so what is a red dwarf exactly? Number one, it's a normal main sequence star, converting hydrogen to helium. It is the least massive, very slowly converting hydrogen to helium. However, it does so slowly that no star is thought to have transitioned from a red giant to a red dwarf in only 13 billion years, which is the age of our universe. So bottom line is these little M dwarfs or red dwarfs are expected to last 1 trillion years or more. They could match the national debt, but we won't go there. And that brings me to another handout. I have a second handout up here, which you're free to take with you if you wish. I'll have a slide of it, but it's always better to have something in your hand you can look at your leisure. This red dwarf happens to be the most common star in our galaxy, and therefore probably other galaxies as well. More to come on those, okay? They are dangerous They may be small and they may be cool, but they're also dangerous for a couple reasons. We'll get into that a little later. Now, a white dwarf, that is the hot remnant, if you will, the core of a star, and it is a compressed core that has ejected its outer layers into a planetary nebula. Again, that's a beautiful feature that would be a nice second or third talk somewhere along the line. Mostly carbon and oxygen. They are very hot, typically 50,000, this is surface temperature now, 50,000 kelvins, and it slowly radiates all that energy into space. There is no new energy in its core. That means eventually it's going to cool down. Okay? Most of these white dwarfs are too dim to see unless you have a telescope and know exactly where to look. And I'm going to show you where to look in several cases here. Eventually, white dwarfs are going to blink out like somebody shut off a light because they just get gradually cooler and cooler and cooler until they disappear from view. At that point, they would be called a black dwarf. Still exists. It's like a giant cinder up there in the sky. And you do not want to be flying through space at nearly light speed and hit a black dwarf you didn't know was there because you couldn't see it. So you have to have short-range radar as well as an infrared scope to see these very dim objects. More to cover on that also. Okay. Examples of a red dwarf. The constellation here is Castor. These two bright stars, Castor and Pollux, are very easy to see. I saw them last night while I was letting my dog out in the backyard. They're slowly sinking down in the west, and they're roughly parallel to the western horizon. But it won't be long before Gemini, the whole constellation, is down. You can't see any of it. But we're going to be talking about Castor, originally given the script A by somebody who was classifying bright stars. And he did the best he could with the equipment he had, but today we know that actually Pollux is a little brighter than Castor. But nobody's going to go back and erase the names Alpha and Beta and all the atlases that are out there. So we deal. Here's a blow-up, or if you will, a close-up of the Castor system. And this was a photograph that was taken, I believe it was the Hubble Space Telescope that took the picture, because it does go a little bit into the infrared, and a lot of the heat coming off of red dwarfs is infrared rather than something we can see visibly. Okay, but Castor A and B are almost twin yellow-white stars. One is magnitude 3 and the other is 1.9, so it's about 2.5 times dimmer than the brighter of them. However, we have discovered that orbiting each of these yellow-white stars is another red dwarf. So we're now up to 4 stars. And then, lo and behold, we also found Castor C. And I saw this with a 6-inch scope. I have a 150 millimeter refractor, a triplet refractor that I use as my main scope. I was able to see this in Homer Glen a couple of years ago when the guy said, hey, pointed at Castor, I don't have enough aperture to see this. But we were able to see a single red dwarf here. Couldn't separate it into 2, but a 6-star system. And other than star clusters, I don't know of any system that has more than 6 stars in it. They become very unstable if you start getting too many stars in there, and some are thrown out of the system. These all seem to be cool because these two are orbiting each other, and these two down here are orbiting the primary star. So it's a fairly stable system. Now, in fact, the brightest star in the sky, the nighttime sky, anytime during the year, is the star Sirius. It is located in the Dog constellation, Canis Major. This is the brightest, so Alpha Canis Majoris would be another way of describing it. But they just will go with its name, Sirius. And Sirius here has a magnitude of negative 1.4. If you've studied the magnitude system, and again, it's hard not to if you've had any kind of an astronomy or physics class in astronomy, the magnitude system is simply a way of saying how bright a star is And the human eye can see stars that are 6th magnitude, 5th, 4th, 3rd, and lower, even into negative numbers. But the human eye cannot see anything that is a number higher than 6. Then you throw in light pollution like we have here in Northeast Illinois, and most of us can't even see a 4th magnitude star. So take that with a grain of salt, or maybe a whole salt mine. This little white dwarf can be seen. I saw it over in Indiana at the dunes just a year before it became a national park, and it was a national lake shore or something like that. Anyway, the secret to seeing it is not get blinded by the A star. So you move your telescope so the bright Sirius A is just out of the field of view that you're looking at, and then you can see this little companion, if you will, that is hugging it and does orbit in about 50 years, orbits the primary. It's only 8 light years away, so that's the reason we can see this thing. Okay. Now, there was an astronomer who decided he wasn't going to compete with all the people who want to study high energy and exciting things like Mars and all that stuff. He decided, I'm going to study stuff nobody else wants to study. So while they're studying the bright and exciting things, I'm going to study the dark stuff in which nothing's going on. As it turned out, those dark clouds form stars in the future. But they're cold, they're dark, etc. They're called Barnard objects after him. And there is such a beast in the constellation Ophiuchus. And Ophiuchus, if you go off of Beta Ophiuchi, here it's a star called Cybele. On any star atlas, you can find 2 stars, 66 and 67 Ophiuchi. Well, put your finger on 66 and move towards Cybele just a tiny amount, way less than a degree. Let's call it maybe 20 minutes of arc. And you can find a little red dim object that is Barnard's star, and that is a red dwarf. Its proper motion is the greatest of any star that's ever been measured, and yet would still take 180 years to cross the full disk of a full moon. So to us, that's not very fast, but to stars, that is hauling because of how far away it is. Okay, so it's a 9.5 magnitude red dwarf, technically within the grasp of binoculars if you're in really dark skies. And again, you know you're looking for a red star. And that brings me to a point that needs to be brought out right here and right now. When somebody says, oh, that's a blue star, like Rigel, your eye may not see it as blue. And if I say Barnard's star is red, your eye may not see it as red. There's a reason for this. The back of our eye has 2 kinds of light receptors, cone-shaped and rod-shaped. The cones we use during the day. They are high resolution, allowing you to pick out on a line of ladies at the other end of a football field. You could pick out your grandmother because it's high resolution. You recognize her, okay? And you also get all the colors of the rainbow using the cones. But they're nearly worthless at night. At night, the cones essentially don't work. That means most of the color you would have seen, you're not going to see. Rods see all kinds of subtle things, but they don't show color well. So you're looking at Rigel, supposedly a blue star, and you see it as a white star. That's just a function of how our eyes work. So it's not that you're doing something wrong. It's just your eyes cannot be high resolution and work in the dark when it's designed to work during the daytime. Okay, so Barnard's star, a very close, in fact, it's the second closest star to our sun, and it's a little red dwarf. Now, this is shown to scale with our good buddy Jupiter off to the right. Keep in mind, Jupiter has a diameter of about 88,000 miles, 11 times Earth. And Barnard's star, despite being a small red star, is still bigger than Jupiter. And it is much more massive as well. This is the name of the astronomer who found a red dwarf all by itself. And it's found in Ursa Major. I'll show you shortly. This one is the 4th closest star to us, and it's a little over 8 light years away. This is Ursa Major, if you will, the Big Bear. or if you like, the Big Dipper. And down the hind leg of the Big Dipper, you go to Splitsville. This is the front back leg. This is the trailing back leg. And Lalande 21185 is way down here near Tania Borealis, which is a star, usually has a name in star atlases you might have. So if you want to find something that's not too far away, this one is actually easier to find because the secret here, put in a low power eyepiece and go from Tania Borealis up a little over to the right and look for the reddest star in the area and you've nailed it. I've seen this a dozen times, but to be honest, it's not terribly exciting. It's dim, it's red, it's there. Okay, that's about all we can say. Now, one system that is a whole lot more interesting is this one. It is around a star called TRAPPIST-1. And TRAPPIST-1 has 7 exoplanets. We have shown a graph here. This is our solar system, and the spacing isn't perfect, but close enough. These stars up here are closer to TRAPPIST-1, a red dwarf, than Mercury is to our sun. And if we start with Earth and go up here, there are 4 different exoplanets closer to the sun than our Earth. But that's not always bad. Raise your hand if you've ever been camping near a campfire. Does it matter if the fire is big or small? If it's small, you just move your sleeping bag a little closer. And hopefully you have somebody playing fire guard so your sleeping bag doesn't catch fire. You don't want to get too close. I have seen people, I spent 3 years in the Army in Alaska for a year and a half. People would put their sleeping bags within 2 feet of a fire to stay warm at night when it's 35 below zero. Then in their sleep, they roll over and roll into the fire. It's not good. They stay plenty warm, but the whole idea is if you're the fire guard, you have to pull that person away and throw snow on him until the fire goes out. So this is a very cool star. It's okay to exist closer to it. And the hotter the star, the farther away you can be. Sort of the same idea as that pudding we know who the 3 bears got into. Okay, red dwarfs apparently seem to be good for having lots of planets, exoplanets. But they have 2 major problems. One of them, and oh, by the way, red dwarfs do make up 3/4 of every star in our in our galaxy. 3/4 of them. And this was done by a series of photographs that were analyzed more than a few hundred at a time through their spectroscopes with the Harvard, the Hooker, and the 48-inch Hale telescope out in California. They studied hundreds of thousands of stars, and the breakdown this to their spectral class had red dwarfs win by a large margin. 76% of all stars are these little red dwarfs. But they have 2 problems. One is tidal locking. There's a tendency for it to be in a relationship with the star so that it latches onto the planet and won't let it wobble. It's a lot like our moon is to us. One side of the moon stays facing the Earth at virtually all times, and I'm disregarding librations, got to put that R in there. Librations do allow a slight rocking back and forth. Okay, so tidally locked, if that's the case, one side is going to be very, very hot, the other side is going to be very cool, and some astronomers say, so what? At the poles, it would be somewhere in between, it might be livable. True, we think. And then the other, which is probably deadlier, red dwarf stars being convective are subjected to flaring. And a flare can blast the atmosphere right off of a nearby planet. We have just in the last week undergone some class M flares, and they've been talking about the possibility of seeing northern lights, even as far south as this part of Illinois. So we do have some, but red dwarfs are even more flary than our sun is. So those 2 things sort of reduce the possibility of life as we know it. And I always have to say this, life as we know it. We don't know anything about life that we don't know about. We always think that carbon is the only way that we can have living organisms. They have to be carbon-based. We don't know that. That's an assumption. And you know what happens when you assume. Okay, where is TRAPPIST-1? It is in the constellation of Aquarius. This is the plane of the ecliptic, the blue line. That is the path the sun carves out or creates as it orbits through the constellations. And all of the planets and the moon are pretty close, although not exactly on the ecliptic. So it is way up here in the eastern part of Aquarius for people who want to go hunting for this. I wish you luck, because TRAPPIST-1 is very dim, so you need a pretty good sized telescope. And here are some of the stars that I've talked about, not all of them. I didn't talk about Proxima Centauri, the closest red dwarf to us, because it's in the southern hemisphere. I picked 4 that you could go out tonight with a good telescope and you could find all of these. So I picked them because observers that I usually talk to at star parties and so forth like to go out and find these targets, okay? Jupiter, TRAPPIST-1, this one we didn't discuss, southern hemisphere, Proxima, southern hemisphere, and notice Lalande 21185 is much larger than the others. Believe it or not, it's lower mass. The more mass it has, the tighter it squeezes it into a smaller ball. So the smallest red dwarfs, may have more mass than the much larger red dwarfs, just the way mass works and gravity out there in space. Here's a very unique target. It's called the Blinking Planetary, and it's got a code. That's the new general catalog. This is object number 6,826 in this catalog that has 7,840 targets in it. Well, most go-to telescopes, and raise your hand if you have a go-to telescope. 1 person, 2, me, 3, actually I have 2, so 4. The idea with a go-to telescope, you grab the hand control and you tell it, go to NGC 6826. And lo and behold, if you've aligned it properly, the telescope will go and put that target right in the field of view. No work. You don't have to waste a half hour hunting for it. That's one advantage of having a computerized telescope. The disadvantage is it tends to hit you in the wallet more than you want to pay. But anyway, it is out here on the edge of the bird. This is the Swan Cygnus. There's his rear end, Deneb, goes through the middle star, and then down his nose is down here somewhere. So we go out on his eastern wing, and the Blinking Planetary is way out here near the wing. Easy to find with a go-to, not so easy to find with a refractor or something that's manual. You really have to know the sky to find your targets. Now, if you look at it, you don't see it, the white dwarf in the center. If you look away, there it is. You look back at it, and it just looks like a fuzzball. That's the planetary nebula. You look away, the fuzzball disappears, and there's the star. So it blinks as you look back and forth between it. And that's about the only object I know of that has that particular characteristics. Very cool. First time you show somebody something like that, they don't believe it. They think somehow you faked them out. This is what it looks like now with a photograph. And you can see there's a slight elongation of the planetary nebula as the star blew its dust and gas off into space. And this is the core, again, oxygen and what's that other chemistry? What's besides oxygen in white dwarfs? Yes, oxygen and carbon are going to shrink that down. We do not know how long it takes a white dwarf to form after the planetary nebula. We just haven't had enough time to watch it happen. We assume it's a few thousand years. Maybe longer, hard to say, but at a distance of 2,000 light years, when it is a true white dwarf, we're not going to be able to see it. It's simply too far away. And by the way, there's a topic here that I have to talk about, might as well do it now. A white dwarf will continue to shrink until a special property takes over that is known as electron degeneracy, okay? This electron has a negative charge. So does this one. And as you put them closer together, like charges repel each other. So they're not going to want to join into each other. If you put more effort to it, you can only get it so far before the repulsion force stops the collapse. And when it does, you've got a stable white dwarf. electron degeneracy. It works exactly the same way as me standing on this stage. I have electrons in the soles of my shoes. There are electrons in the wood of this stage. My electrons are pushing on that, and that's why I don't fall through the stage or fall off the edge. Try to hit a wall with your fist. The electrons in your fist will be repelled by the electrons in the wall. And if you do it fast enough, you might be able to punch through some plasterboard, but I don't recommend it. The wall hits your fist with the same effort that your fist hit the wall. That's one of Newton's laws, okay? And besides, it hurts, so don't do it. Okay, my favorite target in the entire night sky. The constellation is Eridanus, the river. The best way to find it is start with Orion and Rigel in the bottom, which is essentially his left kneecap, okay? And his left kneecap is right there. You go past the Witch Head Nebula, which is a cool object, and you end up getting a whole line of stars that come along and go around and down into the southern hemisphere and end up at the star Astronar. That is one of NASA's principal navigation stars. They latch onto that one because they can see it in the entire southern hemisphere. But if we go up here, Omicron Ceti, or Omicron 40, that's actually the star in Star Trek that Spock was supposed to be from. That was his star. Bottom line, we're going to take a close-up look at that star, not the one over here called O3, but this O2 right there. That's the interesting one. Okay, I've discussed this, so we will fly past it. This is the Keid system. K-E-I-D is the name of the star. It means eggshells. Don't ask. I have no idea why they named it after eggshells. But orbiting this class K, 4.4 magnitude orange dwarf main sequence star is a white dwarf. And that is the easiest white dwarf in the entire sky to not only to find, but to see. And then the tricky one is to come over, and also orbiting it is Kiad C, which is a red dwarf. But it's down to 11th magnitude, and that is a real challenge. But you're not going to find 3 dwarf stars together that you can put into one field of view through a telescope anywhere else in the sky that I'm aware of. So I see it every time I get a chance. It's just a cool thing. And very slowly, Kiad C is making its way around Kiad A, and so is B, but C is farther out. So what's happening is B and C are gradually closing together as they orbit the main one. So you got an orange dwarf, a white dwarf, and a red dwarf all in one picture. Okay, so here's we have a list, if you will, of what the targets are. The Castor constellation, easy to find. Gemini is the constellation. And the right ascension and declination, for those of you with go-to scopes, you could punch it directly in, or star hopping the good old-fashioned way. Gemini is the constellation. The magnitude is not outrageously stupid because you can see it in binoculars. Not the red dwarfs, I'll tell you that, but you can see Castor A and B. It's 52 light years away, again, relatively close, and part of a 6-star system. Then we have Kiad Eridanus, both a red and a white, 16 light years away, and it's a nice triple star system, different colors in it and all that stuff. Barnard star, pretty easy to find, and has the fastest proper motion of any star in the sky. The blinking planetary is a white dwarf in the making, and you can really exercise your rods and cones if you keep flipping back and forth between the target and not at the target. And I haven't mentioned the phrase averted vision. How many of you know what that is? I see 4 hands. Okay, I will use an example right here. I'm looking at this gentleman right here with a dark reddish purple type of shirt on. But while I'm looking at him directly, I can see 2 people over here just as well. So it's peripheral vision, right? But if when I'm looking directly at something, the light from you is hitting the cones in my eye. Around the cones, distributed, and there's more of them than cones, are the rods. And when you look away from a target directly, the line of sight goes through the eye lens and then into the side of your eye where the rods dominate. So I could see you very faintly. I can see motion, I can see all kinds of stuff if I don't look directly at you, which almost sounds stupid. What do you mean you see better if you don't look at something? Well, try it. Even the moon, if you look a little bit away from the moon, even just a couple of degrees, 3 or 4 or 5 degrees, you can see features on the moon better than looking directly at it. So bright you're going to blind yourself anyway. So, averted vision, worthwhile doing. Sirius B, white dwarf. And it is best between right now and 2025 because the orbit of Sirius B has been plotted and it's getting in this range. It is farther in its orbit than anywhere else, which should theoretically make it easier to see. I saw it in 2018 over at Indiana, and it wasn't terribly difficult. You really do need steady skies and good quality eyepiece. And if you buy a telescope, take the eyepiece that came with it and throw it as far as you can. You need to buy good eyepieces. It's just like, you have a camera? Okay. Do you have a Nikon? If you have a Nikon, you have a good camera. If you have anything else, you want to go with quality, not quantity, but get good quality stuff. Then you'll be able to see what I'm talking about up here. Okay, now, there are friends of mine who have, one has an ultra collapsible 22-inch obsession, another one has a 25-inch obsession. These are telescopes that need a ladder to go up 10, 11 feet off the ground to get the eyepiece. I have a little 38-inch long triplet with a lens in it. I don't have a huge one like that. But if you can afford a big telescope, you're going to look for the faint stuff. Well, with a small telescope, you can look for the faint stuff too. So I encourage people to stop looking at the same stuff you've seen 1,000 times and try to find some of these hard targets. The little baby red dwarfs and white dwarfs. They're kind of fun to nail. And then you can show your friends and they would be just worshiping you because you are so good with your telescope. Okay? Okay, we are done. Any questions from anybody? Questions about anything? Nonsense questions? Astronomy jokes? Anything? Right here. Come on down and get them. I had an elementary class at Beebe School, which is in North Naperville, and I was asked by a third grader, why do stars have points? And I said, well, people just tend to draw those points on them, but they're not really there. And a little Jewish boy raised his hand and says, yes, our stars have 6 points. Now, I didn't argue with him. That's just the Star of David. But that is not physics. Physics will flatten anything into a sphere. The gravity just pulls and flattens everything. So that's the way it works. That doesn't really qualify as a joke, but true story. Anything else? By the way, I appreciated your talk. It was interesting.
All right. So if we don't have any more questions...
Okay, I will pack it up.
Yeah. Well, I guess first, do we have any other questions for our previous 2 speakers? Any at all? All right.
I feel like I've been on candid camera here. This young lady is aiming a big cannon at me here.
All right. Well, I mean, if there's no more questions, can we give one more huge round of applause for all of our speakers
Good
today?
audience.
Everybody did an amazing job, and we are so happy to have finally introduced this type of cosmic conversation to you. And yeah, we hope to have a future event like this again sometime soon. I guess sometime next year.
Speaking of next year, this is off the cuff. This doesn't cost extra. I'm just giving you this as a freebie. April of next year, on April 8th, there is a total solar eclipse of the sun that is going to come about as close to aurora as you're ever going to get. And that is just on the other side of Indianapolis. So in a 3.5 hour drive, you could go there and find a park in some small town and see it. I encourage you to go see it because you don't get to see these every year. In fact, I think the next one after this is 60 years from now. So they're rare, they're incredibly gorgeous, and I highly recommend you talk whoever has a car into loaning it to you and driving over there, or getting a properly filtered telescope and enjoying the eclipse yourself. That's fantastic. Okay, I guess that's yours. So, thank you. Please having to yell.
Definitely. All right. Who's talking first? I don't remember. Yeah. We'll go ahead, George.
I just want to say thank you guys. Thank you everyone for coming out. If we could get one more round of applause for all of our speakers tonight. But yeah, that's basically it, I think. This was, like a test run, so we're really glad everyone seemed to have a good time. And thank you for coming. Anyone else?
We just want to reiterate the same thing. I cannot express, on the behalf of the whole board, how thankful we are for you guys coming out today. It was an amazing test run, and this is only cemented that we're going to keep on doing this in the future. But I want to thank our speakers who were able to come in. Thank you, Mr. Hopkins. Thank you, Mr. Lim, if we could get him back. But we want to say so much thanks and gratitude for all of you guys coming around, and we hope you enjoyed Cosmic Conversations.
Yeah, definitely. And also a huge thank you to Nurse Angie for helping us and being a wonderful advisor for chaperoning this event and preparing this, helping prepare this amazing event.
And then we'd like to give a quick thank you to ISP for all the help that they've done tonight setting this up and, just making sure everything runs smoothly. And yeah.
And then we have, first of all, thank you again to you all for coming, but we have one final thank you to our leaving senior board. You guys have been absolutely amazing. This event would not have happened without you, and it has been a pleasure to serve on board with you all. So thank you guys all for coming. I hope you enjoyed Cosmic Conversations, and have a good night.